The cool guy. All right, so let's get back to it here. So we left off with this problem here. And so they gave you a couple of bases. And so here's how you solve this. What you're going to do is you're going to draw the conjugate acid of each one of these. So the conjugate acid for this one would be this compound. This is called acetylene. It's used in an acetylene torch. Now the pKa of acetylene, it has a bond between an sp hybridized carbon and hydrogen. The pKa is around 25. Okay, that's the pKa they gave us in the table. And then the conjugate acid of this is NH3. I'll just write it like this. And the pKa of ammonia that they gave us in the table was 38. So we can see that ammonia is the weaker acid. So I'm going to put here, we'll put here weaker acid. Therefore, this ion, the NH2 minus ion, this is going to be the stronger base. You notice that the nitrogen has a negative charge, so you should remember that it's missing 2 lone pairs on it. There's a lone pair missing here too. So again, that's our rationale. The weaker acid gives us the stronger conjugate base. You guys want to hear a funny one? This ion, the NH2, I might have told you this already. I repeat myself a lot, but the NH2 minus ion, that's called an amide ion. Okay, I know that there's a functional group too called the amide. I taught it to you. Okay, later on, or earlier on. I'll just draw it like this, a secondary amide. But I know that that's an amide as well, so it gets a little annoying sometimes to remember too, but eventually you start to flesh out the ideas. Anyhow, so let's take a look at the next two. So we have a tert butoxide ion and ethoxide ion. So this one takes a little bit better memory, but if we draw the conjugate acid of this, we get tert butanol, and the conjugate acid of this, we get ethanol. Not a big difference between the pKa's in these two, but the pK of tert butanol was 18, and the pK of ethanol was 16. And so since this is the weaker acid, so we'll put up here, we'll put weaker acid. Therefore, this is going to be our stronger base. So you see how memorizing pKa's can really get you out of a bind. Another thing you can do with pKa's is when you have an equilibrium like this one here, and if you can figure out what the acid and the conjugate acid is, all you have to do is compare their pKa's, the acid and the conjugate acid. Look at the pKa's. Whichever one is the weaker acid, the equilibrium is going to lie to that side. Okay, this is one of the major points in all of organic chemistry, is the equilibrium is going to lie to the side of the weaker acid. Well, if you say, well, you know, what if I get in a situation where I don't know a pKa? Okay, well, there are ways to do that, which we'll take a look at in a second. But if you look at an acid and a conjugate acid, and there's a huge difference in the pKa's, well, in that case, you don't even have to draw an equilibrium arrow. Okay, we see here the difference in pKa values is 34. Okay, we have our acid, which is water, which is 15.7, and our conjugate acid, which is an alkane. Remember that this carbon here is sp3 hybridized. So there's a huge difference. In that case, we don't even write the arrow in the opposite direction. It's totally irrelevant, okay? We only do that when there's a small difference between the two. All right, so if you get stuck and you can't remember the pKa, what do you do in that case? Well, I've got some great news. Is you can also look at a qualitative perspective. So this means not memorizing a number. It means making an educated guess, okay, by studying the compound. And this is something that organic chemists do every day. What if you see a brand new compound you've never seen before? Sometimes we just make an educated guess about what the pKa of a proton is, or whether it's more acidic or less acidic. So it says here, to determine the relative strength of two acids without knowing their pKa's, we actually don't look at the acids, we look at their conjugate bases, okay? Why do we do that? Because after the acid has donated a proton, think about what an acid is supposed to do. Once the acid, HA, has given up its proton, you're left over with A minus, okay? The conjugate base. So I'll just write here minus H plus. You look at the conjugate base and say, how stable is this? If it's really stable, that means it came from a strong acid because it's comfortable with that negative charge. If it's not stable, that means it came from a weak acid, something that did not want to donate a proton. And so essentially, we study the stability of the lone pair, If the lone pair is stable, it came from a strong acid. If it's not stable, it came from a weak acid. Now let me show you the way that we do this using the David Klein textbook. Remember, the author of our textbook is Dr. David, so I'll just say Dr. David E. Klein is his name, okay? Wonderful organic chemist, and he actually developed this, okay? This idea of what we call aereo, okay? I studied organic chemistry. The textbook that I used, 30 years ago, was called Seihan Egi, okay? And she did not have this in her textbook. But here we go. So what he does is this, is he says, the more effectively a conjugate base can stabilize negative charge, the stronger the acid. And here are the four main factors that affect the stability of negative charge. The first one is, what's the type of atom that carries the negative charge? The next thing we look for is resonance structures. Well, the next thing we look for is induction. So that's if we have an electron withdrawing group. And the last thing we look at is the orbital, sp2, sp3, sp, etc. So we have A, R, I, O. You put it all together, what do you get? Aereo, okay? And this is, again, something that was developed by the author of our textbook. So let's take a journey through it. And you're going to see how this works really well, not all the time, but most of the time for evaluating acidity. So let's take a look here. Aereo. So we're going to start with atom. If you look at these two conjugate bases, okay, one has a negative charge on a carbon, which is here, and the other one has a negative charge on an oxygen. Well, if we compare these two atoms, we know that they're in the same group, the same period. So we have boron, carbon, nitrogen, oxygen, fluorine, like this, okay? These are in the same period. These are in the second period, okay? We're comparing a charge on carbon and a charge on oxygen, negative charge. Which one is more electronegative? Well, you guys should know that carbon has an electronegativity of 2.5 and oxygen is 3.5. So which one is more comfortable bearing the negative charge? The answer is the oxygen. So it's more stable. So what does that mean? It must have come from a stronger acid, right? So if we look at the conjugates, okay, if we draw the conjugate of this, we get an alcohol, and the conjugate here, we get an alkane. So an alkane has a pKa that's equal to 50, and an alcohol has a pKa, we'll just say it's roughly around 17. So obviously the alcohol is much, much stronger of an acid, and so that's why its conjugate base is more stable. So when we're comparing a negative charge on two elements that are in the same period, we use electronegativity. I'll highlight that for you. If they're in the same period, we use electronegativity to determine which one is going to be the most stable conjugate base. If the atoms are in the same, if they're in the same group, okay, if you were to let's say compare fluorine, if you were to compare, let's say fluorine, chlorine, bromine, and iodine, so if they're in the same group, then we use the atomic size, okay? So we'll use size is used if they're in the same group. So what does that mean? It means that HCl would be a stronger acid than HF. It means that HBr would be a stronger acid than HCl. Why is it? Because size increases, okay? So we'll put here larger and smaller. So the bigger the ion, the better it is at stabilizing negative charge. And we see that right here. So now, if we were to compare water versus hydrogen sulfide, so if we compare water, which is H2O, okay, versus H2S, and we want to know which one is a stronger acid. What do? We look at their conjugate bases. That's what this whole section is about. So let's draw the conjugate base of water, which is a hydroxide ion. Oops. Hydroxide ion, like this. And then if we draw the conjugate base of hydrogen sulfide, we get a hydrosulfide ion. So there we go. So now we see that the negative charge on one of them is in an oxygen and the other one is in a sulfur. So which atom is going to be better at stabilizing that negative charge? Well, we see that oxygen and sulfur are in the same, they're in the same family or the same group. So we do not use electronegativity. We use size. So same group, therefore use size. Okay, and sulfur is larger. So we'll put here larger, therefore better at stabilizing negative charge. Okay, I'll just put negative charge like that. So that means that this is a more stable base. So more stable, it has greater stability. So that means it came from the stronger acid. So therefore, this must be a stronger acid. There we go. So now if we actually go to a reference guide somewhere and we look up the pKa's of H2O versus H2S, I'll give you the answers. I'll write them down in kind of running out of colors here, but I'll use the green pen. The pKa of water is 15.7, which you saw from the table, but the pKa of this proton is actually 7.0. So you can see that H2S is a stronger acid than H2O. Give me a thumbs up if you're with me on atom. When they're in the same group, or same period, we use electronegativity, but when they're in the same group, we use size. Great. So there you go. So that's the first one. So we've covered A, like the movie Seven, right? We just crossed them off here. Okay. So the next one is resonance. Okay. So if we were to compare ethoxide versus an acetate, okay, which one comes from a stronger acid? Okay. So in that case, like if we were comparing their conjugate acids, so if we're comparing ethanol and acetic acid, well, you probably would guess that acetic acid is more acidic by its name, that it's called acetic acid, okay? But anyhow, if we draw their conjugate bases, you see that ethanol produces the ethoxide and acetic acid gives you the acetate ion. If you start with ARIO, you can't use atom in this case because the negative charge is on an oxygen in both cases. So then you go to the next factor, which is resonance. What does resonance do? It stabilizes a conjugate base. Here you have no resonance structures for the ethoxide, but for the acetate, you have a total of 2. So that means that this is more stable, right? It says it right here, more stable. So if it's more stable, that means it came from the stronger acid. So what's our conclusion is that resonance can stabilize a formal charge. So therefore, if the acetate ion is more stable, that means it came from a stronger acid. And if you compare the pKa of acetic acid and ethanol, the pKa, if we just write down approximate values, we'll put here pKa for acetic acid. It said 4.75. We'll just write 5. And the pKa of ethanol was around 16. Okay, so you can see clearly that acetic acid is more acidic. So every once in a while, I'll get to this point with my students, and somebody will say, do I have to use ARIO every time? Couldn't I just use the pKa values if I memorize them? The answer is ideally, I would actually try to use pKa values first. Okay, I would only use ARIO when I have to. Okay, but it is a useful tool, and you will be tested on it. So the next one, after A is done and R is done, is induction. And remember, inductive effects are caused by electron withdrawing groups. And so if you were to compare acetic acid and trichloroacetic acid, well, if we look at their conjugate bases, I'll draw them out here. The conjugate base of acetic acid is this. Okay, it's the acetate ion. I'll just draw a condensed version of the conjugate base of trichloroacetic acid. So we have the negative charge here. I'll just condense it, CCl3, like that. We can't use atom because the negative charge is on an oxygen in both cases. I left my lone pairs out here. We can't use resonance because they both have 2 resonance forms. So then we go to induction. Well, you see that trichloroacetic acid has all these chlorines that are going to pull electron density away like that. What does that do? It stabilizes the negative charge, right? I didn't draw the bonds explicitly here, but you have this huge dipole going this way, which pulls the negative charge in and helps stabilize it, okay? It's not as pronounced as an effect as the atom or the resonance, but it is important. And so, again, that's why we always go to atom first. If we can't use atom, we go to resonance. If we can't use resonance second, we go to induction third. Give me a thumbs up if you're with me on the idea of induction. Is everybody with me on that idea? Okay, I want to show you one more thing about induction, is that it's actually an additive effect as well. If you look at acetic acid, it has a pKa of around 5, but as you start adding chlorines, look what happens. You add 1, it's got a dipole. The pKa goes down by about 2, okay? You add 2 chlorines, now it becomes even more acidic, and if you add 3, holy smokes, okay? it keeps getting lower and lower and lower. And I think that in my video that I posted and asked you to watch, I think I do a comparison of trichloroacetic acid and trifluoroacetic acid, right? You guys know that fluorine is the most electronegative element in the whole periodic table. And so these are humongous, just gigantic dipoles here. And it turns out that the pKa of trifluoroacetic acid is actually 0.23. So it's borderline a strong acid, okay? Trust me, we call this TFA. It's strong enough that if you get that on your skin, it will burn it immediately, okay? So very, very strong acid. You want to be careful with that. However, what about vinegar? Are you worried about getting vinegar on your skin? I'll be honest with you guys. I've even consumed vinegar, even ate it, okay? And I was okay. I'm being kind of silly here. But vinegar is a carboxylic acid, but its pK is much higher, and therefore that's why we're not worried about getting vinegar on our skin. All right, so we've covered atom, resonance, induction. What's the last one? The favorite, right? Orbitals. Okay. So everybody here knows the difference between sp3, sp2, and sp hybridization. So sp3 is when your carbon has 1, 2, 3, 4 single bonds. sp2 is when the carbon has 2 single bonds and a double bond. And then sp, there's a couple of scenarios, but the most common one is when you have 1 single bond and 1 triple bond. And so if you have a bond to hydrogen between these hybridization, what happens is that the pKa changes, and you saw this in the table. You go from a pKa here, which is 50, and then here the pKa they gave us, I think, was 44 in the table, and the pKa here they gave us was 25. So we see that the relative acidity changes a lot with orbital. Well, why would that be? Well, it's actually kind of shown here in this picture that as you go from an sp3 to an sp2 down to an sp hybrid orbital, they actually get smaller and smaller. And so as they get smaller, what that means is that in the conjugate base, the negative charge will be closer to the nucleus. What's the charge of a nucleus? A nucleus is positive. So the closer the negative charge is to the nucleus, the more stabilized it is. And so that's why if the conjugate base is more stable, it came from a stronger acid. And so that's why the pKa of this bond is much more acidic than the pKa of this bond here. And that's all it is. It's nothing more than that. So if we take a look at these conjugate bases, and this is good practice, you know, drawing these out, the conjugate base of ethane would be this. I'll just scribble it down kind of quickly here. But if you lose 1 proton, then you get a carbanion. If you draw the conjugate base of ethylene, you get another kind of carbanion. And if you draw the conjugate base of acetylene, I'll just draw it like this. You get another kind of carbanion. But what's the difference between these? This carbon is sp3. This carbon is sp2. And this carbon here is sp. So smaller orbital. This is better able to stabilize that negative charge. This one is bigger, so it has a harder time stabilizing it. And that's why an alkyne is so acidic. Okay. In fact, this isn't really pertinent to the chapter, but you guys like learning about organic chemistry. You guys want to know? I don't know if I've ever told you this or not. We're just starting the subject. But if you want to know how to win a Nobel Prize in organic chemistry, the way you can do it is if you develop a new way to make carbon-carbon bonds. And if you're like, am I hearing you correctly? If I can find a way to make a bond between 2 carbons, I can win a Nobel Prize? Pretty much, okay? And if you're thinking, well, come on, carbon-carbon bonds are the most ubiquitous bond in all of organic chemistry. That's true. They're very difficult to make. However, the first time you'll learn how to make carbon-carbon bonds will be in Chapter 9 in this class. And we're actually going to use the conjugate base of an alkyne. So we'll take this and deprotonate it to make the conjugate base like this, and we'll use that to make our first carbon-carbon bond. So just something to look forward to later on in the semester. All right. Now, again, Aereo was developed by David Klein, okay? It's just a rule that we can generally use, okay? Moses did not come down from Mount Sinai with 2 tablets that said Aereo on them, okay? It's just a general rule. Can we use it a lot of the time? Yes. However, there are exceptions to it. It even says here in your notes, your instructor posted this. It's not 100% reliable. Okay, there are exceptions to it. Again, if you use it, it's probably going to work greater than 90% of the time. But there is one exception that our book goes over explicitly, so I expect you to know this one exception, okay? So I'm going to write this down here. Know this exception. Okay, it's this reaction right here. If we take a look at this reaction, okay, we have acetylene, which is behaving as an acid, okay? This is our base. This is our conjugate base. I'll just write C base. And this is our conjugate acid. I'll just write C acid, okay? Now, if we were to use Areo, forget about these numbers. Forget about the pKa values that are on here. If you were to use Areo, what would you say? You would say, here I have a negative charge on a nitrogen, and here I have a negative charge on a carbon. Nitrogen is more electronegative than carbon. Therefore, the equilibrium should lie to this side. You'd be wrong. Okay, so Areo doesn't work in this case between an alkyne and an amine or ammonia. It doesn't work in this specific case. How do I know that? Well, take a look at the pKa's. If we look at the pKa of the acid and the conjugate acid, you can see that ammonia's pKa is way higher than the pKa of acetylene. And so the equilibrium actually lies to the right in this case. So what's the conclusion is right here. If we had judged by conjugate base stability, if we had tried to use Areo, in this case, we would have concluded that the negative charge on the nitrogen is more stable based on electronegativity. We would have predicted that the equilibrium lies to the left, and we would have been wrong. Okay, now what's our conclusion? Okay, so students get nervous sometimes. They say, well, you would have been wrong if you'd used Areo. It says here for some acids, like this example that I asked you, or this exception, you simply need to know pKa values. And this is why it's so important to memorize table 3.1. So I'm going to put another plug in here for table 3.1. You want to memorize that table. It's going to avoid so many problems. Okay. Now, if you're wondering, are you going to ask me an Areo question where with an exception outside of this one, this specific one here? The answer is no. Okay. If I asked you to solve this using Areo, you can use the rules except for in this one specific case. All right. So there you go. So now it just says here, it says predict which proton is more acidic in each of these compounds. You know what I like about this problem is that you can kind of solve some of them using Areo and maybe pKa for some other ones. Okay, let's start with pKa's, and I'll show you how fast the problem goes if you use pKa's. If you remember that the pKa of a phenol is 10, and the pKa of a carbon between a carbon that is sp2 hybridized and a hydrogen is 44, you're done. Okay, you see that the one in red is the more acidic one, right? Give me a thumbs up if you're with me on the pKa memorization. Like, Mr. Dion, I memorized them all already. You don't need to coach me on it. Good. Okay, awesome. But if you used Areo, which one of those letters would you use to solve this problem? Well, the answer is A, right? You'd use A, and you'd be correct because the negative charge, once you draw the conjugate base, the negative charge on an oxygen is much more comfortable than the negative charge on a carbon. Good. The next one, I would use Areo. So if you remember the 1,3-dicarbonyl, it had a pKa of around 9. Okay, we'll just put 9. And this one here is a ketone, and it had a pKa of around 19. So there you go. You can see that this one is the more stable, right? So that one must be the more acidic proton. But then if we think of Areo, A-R-I-O. Could anybody tell me which one of those letters you would use to solve this one? It can't be atom, right? Because the negative charge would be on a carbon in both cases. So which one would exactly? Thanks, Rubio. Right, you'd use resonance, wouldn't you? Right, because with this one, with the one I have highlighted in yellow, you can draw 3 resonance forms, or the negative charge on 3 positions, whereas the blue one, you can only draw 2 resonance forms. All right, so thanks. Good. And the last one, again, I would totally use pKa's to solve this guy. I'd say the pKa of a carboxylic acid. It said 4.75 in our table. We'll just say 5. And the pKa of an amine was around 38. It's close enough. pKa equals 38. So you can clearly see that this one is way more acidic. And in that case, you got A, RIO. You could totally use atom, right? The negative charge on an oxygen is going to be more stable than the negative charge on a nitrogen. Why? Because we have carbon, nitrogen, oxygen, fluorine. They're in the same period, and oxygen is more electronegative than nitrogen. And there you go, my friends. All right, there's one section here that was put in the latest edition of the textbook, and that deals with cationic acids. So if you have an acid that has a positive charge on it already. So in section 3.4, what did we do? We looked at uncharged acids, and then we looked at their conjugate bases, okay? So this is basically a summary of what we did in aereo. But aereo, like I said, you don't use it all the time. Sometimes you use conjugate bases, or sorry, you use pKa's. But what if you have an acid that's a cation? Okay, if you're like, what do you mean by a cationic acid? Do you guys remember this ion? Who remembers the ammonium ion, right? That's a cation, okay? So that can donate a proton. It's not a strong acid, but it can donate a proton. So that's what we're referring to. So what if we compare the ammonium ion? This is ammonium, not ammonia. This is ammonium, and this is hydronium. Okay, these are both cations. Okay, there's no arguing that. But which one is more acidic? So what we're going to do is we're going to look at the positive charge and look at the element that it's on. Which one of these two elements is going to be more comfortable with a positive charge? Well, I would ask myself, which one of these is less electronegative? Exactly. Thanks, Isaac. You're absolutely right. So what Isaac said is, well, the electronegativity of nitrogen is 3.0, but oxygen is 3.5. That means the oxygen doesn't want a positive charge at all. How would it get rid of that positive charge? Would be by donating a proton. So if it acted as an acid, it would be, that's way more comfortable, right? So that means that the hydronium is going to be the stronger acid. So if you have two cationic acids and the positive charge is on two different atoms, in that case, what do? We look at electronegativity and we solve it that way. So what if you have an example? So sorry, here's the answer. The pKa of the ammonium ion is around 9, and the pKa of hydronium is around -2. So you can clearly see that hydronium is much more acidic, so we covered that one. Okay, so let's move on to these two. These two are a lot trickier, but for my students who are interested in things like MCAT, okay, this is like a classic MCAT question, okay? Is asking you which one of these is more acidic, okay? So in that case, if you don't have the pKa memorized, now you can memorize the pKa of these, and I do have a little table in just a few minutes, but let's say you forgot it, okay? What do you do then? What you do then is you look at their conjugate bases. So if this loses a proton, there's your conjugate base. So if this is our acid, this would be our conjugate base. And if this is our acid, this would be our conjugate base. So we look at the two conjugate bases. Whichever one is the weaker base is going to be the stronger acid. Do you guys remember the definition of a Lewis acid and a Lewis base? So a Lewis base is going to be an electron donor. So whichever one of these is a weaker base is going to produce a stronger acid. So now we look at the pair of electrons. You have a pair of electrons on this nitrogen and a pair of electrons on this nitrogen. I'll do this one in red. If we think about the lone pair in blue, those are localized, right? There's no resonance structure you can draw for this. But what about the arylamine? Could you draw a resonance structure for it? Yes, you can start by drawing resonance structures like this. And so we know that that lone pair is delocalized. So we'll say delocalized. So what does that mean? It means that those electrons are less available because they're not just sitting on that nitrogen. They're actually delocalized throughout the entire molecule. So what does that mean? It means that the arylamine is going to be a weaker base. It's going to be a weaker electron donor, and therefore it's going to produce the stronger acid. So this should be the stronger acid of the two. And that's our conclusion. So again, just a rehash, okay? We look at the conjugate bases, and then we say a weaker base is going to produce a stronger conjugate acid. So again, we'll just write here, weaker, since lone pair is delocalized. Delocalized, okay? And if you want to put in brackets resonance, if that helps, resonance, that might help you get through it. Now, if you look at the pKa's, you can clearly see this is a pK of around 5, this is around 11. So yes, the arylamine is definitely going to be a weaker base because it produces a stronger cationic acid. Now, if you're really good at memorizing pKa's, I strongly suggest memorizing this table. It'll get you out of a bind. And there's really only two numbers that you need to know from it, okay? The first one is if you have a protonated amine, whether it's ammonium or any kind of amine, the pK is going to be in the 9 to 11 range, okay? If you have a protonated arylamine, so aryl ammonium ions, they have a pK that's around 5, and that's going to get you anywhere you want to go. So again, an ammonium ion is going to give you a pK of around 9 to 11. So you could even say 10. It's going to work. And then if you have an aryl ammonium ion, it's going to have a pK of around 5. This will help you when you study things like peptides and proteins too, because you look at the pK of those at physiological pH. So one more thing to touch on before we move on to the next section, which is you guys remember the functional group an amide, okay? Sometimes students will look at the lone pair on a nitrogen in an amide. So if I just redraw the amide without the resonance arrows, and they'll say, oh, this must be a good base, right? Because it's got a lone pair on a nitrogen, just like an amine. It's actually a terrible base. Okay, it's not basic whatsoever. Why? Because that lone pair is delocalized across all of this, right? You see the lone pair is down here, and then it's up here too. So it's delocalized, and therefore, if it's delocalized, it's not localized, and therefore, amides do not function as bases. You can almost memorize this. An amide functional group is never going to function as a base. All right, so let's go back to this idea of how do we predict the equilibria when you're on a quiz or an exam. How do you predict the equilibria? Is the equilibrium going this way or is it going this way? Well, what do? You got a couple of choices, okay? Number one, your best option is always to go with pKa. If you know the pKa, you don't have to think about aereo at all, my friend. Just forget it. Don't even worry about it because you don't need it. If you know pKa's, you're in the clear, baby. You're good to go. But if you don't know the pKa values, in that case, you would use aereo. Okay, so you would look at aereo. You would look at the stability of the conjugate bases, and you'd make a judgment call based off of that, no pun intended. So now, let's take a look at this question 3.27. It says, predict the position of equilibrium for the following reaction. So we have an anion, we have our amine, then we have an alkane, and then we have the amide. This is called an amide ion, not the functional group. So if we think about our base, because this is accepting a proton, the ammonia is our acid because it's donating a proton. This must be our conjugate acid, and this must be our conjugate base. So now let's look at the pKa's of the two acids. The pKa of ammonia was around 38, and the pKa of an alkane was around 50. The equilibrium is going to lie to the side of the weaker acid. And so we take a look at our equilibrium arrows, they should lie to this side. So pKa's are always going to work. But could we use aereo in this case? Let's take a look, okay? You see the negative charge is on a carbon on the left, and the negative charge is on a nitrogen on the right. Which one of those two elements is better at stabilizing a negative charge? Well, remember, carbon and nitrogen are in the same period, and so we go off electronegativity. And so using aereo, we would say nitrogen is more electronegative than carbon. Therefore, also, we would say that the equilibrium is going to lie to the right. So in this case, pKa is always going to work, and aereo would work as well. Both of them are going to be totally fine. There's nothing wrong with either of them. So that brings us to the leveling effect, all right? The leveling effect is only discussed in major detail in this chapter, I would say. It does come up elsewhere in the course, but it's really a concept that you would know already, okay? It's a concept you would know already. Let me go over one concept with you before we get into the leveling effect. If I put, instead of sulfuric, I used sulfuric earlier today. If I put hydrochloric acid in water, okay, do I have any HCl molecules in there? If I put some if I have hydrochloric acid, do I have any HCl molecules intact? The answer is no, I don't. And if you're like, what? So if I look at a bottle of hydrochloric acid, there's no HCl molecules in it? Not really, no. Why? Because what's going to happen is it's going to produce hydronium and chloride ions. And if we compare the acid and the conjugate acid, the acid has a pKa of -7, and the conjugate acid has a pKa of around -2. So the equilibrium is going to lie to the side of the weaker acid. And that, my friends, in a nutshell, is what the leveling effect is, okay? So I'll describe it to you in more detail in just a second. But the bottom line is, for something like the example I'm showing you, is this: that acids that are stronger than hydronium cannot be used in water. Well, they can be. You can actually use an acid stronger than hydronium in water, but you have to know that what you're actually going to have in solution will be hydronium ions. So, because the equilibrium is going to lie to the side of the weaker acid. So, why do we teach this section? It's because if you want to set up a reaction as an organic chemist, you have to know how to choose an appropriate solvent for your reaction. Do I do this reaction in water? Should I do this reaction in an ether? What do I stir my reaction around it? And so the solvent should be able to surround the reactants, allow the reactants to collide with each other, but not react with the reagents, right? You want the solvent to just kind of sit there and act as a vehicle to allow the reagents to collide. So what does that mean? It means we have to understand that because water can act as an acid or base, it does have a leveling effect. So as I described before, acid stronger than hydronium cannot be used in water, and acid stronger than hydroxide, bases stronger than hydroxide cannot be used in water. The exact same rationale would apply here. It's because if you have a base that's stronger than hydroxide, it's going to rip all the protons off of water and just form hydroxide ions. Let me show you an example. Okay, it says here, appropriate use for water as a solvent when the base is not stronger than hydroxide. So here we have an acetate ion. Acetate, okay. This is water, obviously. Then we have a carboxylic acid. So I'll just put here conjugate acid, and this is our conjugate base. So the question is water a good solvent for the acetate ion? Well, if we look at the equilibrium, this is our base, this is our acid. The equilibrium in this case is going to lie to this side, right? It's going to lie to the side of the acetate ion. Why? Because it's going to lie to the side of the weaker acid, 15.7 versus 4.75. And so what's the conclusion that we can draw here is that water is an appropriate solvent for an acetate ion, okay? You can put an acetate ion, this guy here, so that's what this is, in water, no problem. It's going to stir around and you're just going to say, hey, look at that beautiful solution of acetate in water. Because water can act as an acid or a base, again, what if you put sulfuric acid in water and you mix the two together? Is water an appropriate solvent to dissolve H2SO4? The answer is no, not really, because sulfuric acid is a pK of -9, whereas hydronium is a pK of -2. And so the equilibrium is going to lie hard. Is going to lie hard to this side. So you're going to have no sulfuric acid molecules intact. None. They're all going to be converted into hydronium ions. Now, again, going back to this idea here, it says bases stronger than hydroxide cannot be used in water. For example, you wouldn't be able to perform the following acid-base reaction in water. Let's take a look. So what the question is saying, or what the concept, or I guess it is a question, if you were to mix these two, okay, there's nothing wrong with mixing these two reagents, this amide ion with the acetylene, okay? In fact, it's actually a good idea because the pKa of this proton is 25 and the pKa here is equal to 38. So there's nothing wrong with the idea, okay? It's just asking you, could you do this reaction in water? Okay, and the answer is no, you can't. If you're looking at it and saying, well, the reaction looks good, the equilibrium should lie to the side of the weaker acid, so that looks good to me. You're right. The equilibrium, the pKa's are set up correctly. The problem is you could not use water as a base. Why? What's going to happen is there's going to be a reaction occur between the water and this base. Let me show you. Okay, if we write out the amide ion, which is negatively charged, plus water, what's going to happen is it's going to rip a proton off the water to give you a hydroxide ion plus an amine. Now an amine is, so this is our base, this is our acid, this is our conjugate base, and this is our conjugate acid, like this. So now let's compare the pKa's of the two acids. Water has a pKa of, we'll just put here 16, 15.7, and then we know that an amine, as we see up here, has a pKa equal to 38. So the equilibrium is going to lie to this side. So what does that mean? Is that this base is going to be destroyed by the water. It's just going to rip all the protons off. Give me a thumbs up if you're even like 60% of the way with me on that concept. Any questions about that one? Okay, this is one you're going to have to read and try it yourself a couple times before you master the idea of the leveling effect. But because I don't suggest memorizing this here, a lot of times students do, and there's nothing wrong with it. But if your brain is already full enough, you can just kind of figure out using pKa's and area. But the crux of it is acid stronger than hydronium. They're just going to produce hydronium ions, and base is stronger than hydroxide are just going to produce hydroxide ions anyway when they're in water. So let's take a look at solvating effects. So now we're kind of getting to the end of the chapter, and he just stuck a couple of last minute concepts that you need to know. The next one is solvating effects. And this is something that we actually looked at briefly already this course, is if you look at these two, tert-butanol and ethanol, how do you rationalize that ethanol is more acidic, okay? It's got nothing to do with atom. It's got nothing to do with resonance. It's got nothing to do with induction. And it's got nothing to do with orbital, right? You can't use any of those. So in that case, what do? Let's take a look at the conjugate bases, and you see that the conjugate base here is going to look something like this, and the conjugate base here is going to look something like this. So how do we justify that ethanol is 100 times more acidic? Well, it's because there's way too much steric hindrance here that you can only get a little bit of solvent around this negative charge, but there's very little steric hindrance here, so you can get a lot more negative charge around this oxygen. And so that's called a solvation effect. It better stabilizes the negative charge, and you can see it shown here in the slide. Because we can put way more solvent molecules around the ethoxide, this negative charge is going to be better stabilized, and therefore it's going to be a stronger acid. And that's all there is to it. So if you're wondering, well, how much are you going to ask me about the solvation effects? Really, I think this is about the only kind of example that I'll come up with is something that involves an alcohol like this. Last thing is, if you're second to last thing rather, is if you're very astute, which I know you all are, you probably noticed that in a lot of these mechanisms, you're looking at this reaction and saying, where's the cation? You keep drawing these reactions and there's no cations anywhere. Where are they? Okay, because you can't just have negative charges floating around. Well, the answer is, and I'm sure you've picked up on this already, is that oftentimes in organic chemistry, we just leave the cations out. Okay, we just leave counter ions out. Those are spectator ions. They don't participate in the reaction. And so we leave them out all the time in organic chemistry. It says at the bottom, counter ions oftentimes left out because generally they don't play a role. Are there times in organic chemistry where you have to look at the cation? Yes, absolutely. But you can even see here in the notes, very, very few exceptions in this class. I don't even know if there is an exception in Chemistry 3101. I don't think there is. So and again, this is more just like kind of an FYI thing, But it's one of those things. I remember one time I was teaching this and the student said, I kept wondering, but I didn't want to ask. And I said, well, never be afraid to ask, number one. But number two, there's your answer, okay? That's why we leave it out, is because the cations oftentimes are spectator ions and they don't participate in the reactions. But they are there, okay? We just don't write them out. And the last concept in chapter 3, which I already mentioned, is a Lewis acid and a base. This is a definition, or two definitions that you would have had to memorize in general chemistry, probably one and definitely two, which is a Lewis acid is an electron acceptor, a Lewis base is an electron donor. And if you remember the whole story, it's because, you know, how do you justify acidity of some compounds that are not proton donors? Well, it's because they can accept electrons. But remember that anything that's a Bronsted-Lowry acid is still going to be a Lewis acid, and anything that's a Bronsted-Lowry base is still a Lewis base. So if you look at this example down here at the bottom, okay, a reaction between water and hydrochloric acid, right? Everybody here would know to say that this is an acid, right? It's a proton donor. This is a base. It's a proton acceptor. This is our conjugate acid, right? It's what accepted the or it's what's left over after the base accepts a proton, and this is our conjugate base, okay? But this is what I just did here. This is Bronsted-Lowry. But if you think about Lewis acid, okay, it says here a Lewis acid accepts a pair of electrons. Well, you can see that if this is our acid, you can see the chloride is accepting a pair of electrons. So this is definitely a Lewis acid. You can see that the Lewis base donates it. Well, there you go. It's donating this pair of protons. So yeah, is that a Lewis base? You bet your Bobby socks it is, right? We'll put here Lewis base. All right, so again, the definition of acid and base, whether it's Bronsted-Lowry or Lewis just broadens the definition is all it does, okay? So you have to remember that a Lewis acid is an electron acceptor. A Lewis base is an electron donor. I think the easiest way to remember this is acid is acceptor. So you have two vowels, the letter A twice. Acid, electron acceptor. And then you have base and donor. So base, where's my blue pen? Come on, blue. You have base is a donor. So two consonants. So B and D. Okay, that's the easiest way to remember Lewis acids and bases. So some acid-base reactions cannot be classified using Bronsted-Lowry. So if you take a look at this reaction here, you can't use Bronsted-Lowry, but it is an acid-base reaction. You can see that the water is donating a pair of electrons. So this is our Lewis. This is our Lewis base. And again, it is an electron donor. And the boron trifluoride is a Lewis acid. Why? Because it's an electron acceptor. And then this funny looking thing over here, that's a zwitterion, right? It has a positive and a negative charge in it. We don't look at a ton of Lewis acids and bases in this class, but you will be tested on the concept on quiz 3 and is pertinent for the course. And so the last question just says, identify the Lewis acid and the Lewis base. Well, you can see that in the first one, you're forming a bond between the oxygen and the aluminum. And so the way you would draw that curved arrow is start on this pair of electrons and end up on the aluminum. So this is the electron donor. So this must be our Lewis base. This aluminum trichloride is our electron acceptor. So this would be our Lewis acid. And in the last one, you see that the oxygen of the carbonyl is picking up the proton from the hydronium. I'll put it on my lone pairs here. So we're going to pick up this proton like this. So we can see that the hydronium is acting as an acid. Why? Because it's accepting this pair of electrons. So we'll put here Lewis acid. And you can see that this guy, the ketone, is donating this pair of electrons. So this would be our Lewis base. And there you go. On the quiz, you will be tested on identifying Lewis acids and Lewis bases. And that covers all of chapter 3.